Hi everyone. So while the others join, let me get started. I will make some announcements and then I will hand it over to Kedar, who will be delivering the majority of the lecture. And then I will come back at the very end for a sort of end of class thing. Right. So today's talk is on video compression by our guest speaker, Kedar Tatswadi. Just introducing. So Kedar did his PhD from Stanford under the guidance of Professor Tsachy Weissman in 2020. He has since worked in Wave 1, which was a startup focusing on compressing videos, and he is currently in Apple. You have heard his name many times throughout the class. He was the one who basically gave birth to this class and to the Stanford compression library, and then Pulkit and I sort of tagged along. And he has been a friend and mentor to both me and Pulkit. So, very excited about this. Without further ado, please.
Right. Thank you all for coming, and thanks Shubham for the introduction. So I think so today's lecture we are going to discuss video compression. Until now in the course you have looked at various modalities starting from lossless compression of text, log files, genomic data and so on. You also looked at image compression. I believe there was a homework on like a question which we designed for the JPEG style compression in the homework 4. Hopefully you have also looked at that. And so we are just going to build upon that, all that knowledge towards the final frontier on probably the most important one in compression, which is video compression. Right? So today's talk will be slightly more higher level, but let me know if there are specific questions and I can go into more details about a few things. All right, so let me get started. Okay, so I think this doesn't need, no one needs any introduction to this slide. Everyone knows that video is growing and innovating, and just based on the amount of video which I consume daily, I mean the amount of YouTube and Netflix and so on, which I myself watch, it's just kind of crazy how much the amount of video being generated, consumed, and these are numbers from a few years back. So it just tells us that the amount of data which we have is just incredible, and of course that's one of the reasons why we really need video compression to work quite well. Right. Okay, so just to give a sense of the video compression or video codecs out there, so you might have heard about these terms here or these codecs here, H.264, H.265, VP9 and so on. So these are different compression algorithms or compression standards for video. H.264 is actually the most common one which you would see. So if you are typically encoding or typically having a video anywhere, most likely it is going to be encoded using H.264. H.264 is today around 20 years old, 15 to 20 years old, but it's still widely used just because I mean it is reasonable at the same time. It's something which is supported on almost all the devices, right? And so these are basically different generations. So H.265 is the newer one, which came maybe around 5 to 10 years back, and H.266 is something which is in active development. So you might not have H.266 today on your devices yet, but it's something which is being added. Right. So this is basically a set of video codecs, and I mean the goal is obviously to take a video and convert it to bits. Right. So that's the goal. And yeah, today we are going to try to understand how they really work. Okay, so one thing which I wanted to actually just to emphasize that how important video compression is. I mean, the thing is that video compression is first so important today, and it's so, at the same time it's so intensive that video codecs have been, both encoding and decoding have been put on silicon. So people have put in the effort and the money to like put a reasonably small but still quite important media engine. For example, this is a snapshot from the M2 chip which Apple has, where part of the chip is actually, part of the chip has a portion which does video encoding, video decoding and so on. So it just tells us how important video compression is, and at the same time also how costly it is, because encoding, decoding does take a bit of effort on your machine, and so putting it on silicon is something which is what makes it tractable. And so there have been n number of PhDs on this, just to make the video codec work, but at the same time optimize it. Optimize it to every millisecond and so on, and then run it on chips and so on. Right? So we are not going to discuss this aspect of the codec, trying to keep it high level today, but definitely there is a lot of literature out there if you want to try to understand how video codecs are implemented on chips and make them run efficiently and so on. Right? All right. So let's try to understand how video compression works. But even before then, let's go to the basics, like what do we actually mean by a video? Right? And the answer is quite simple. I mean, I assume everyone knows this, but the way in which we interpret video, or one way to think about the video, is that it's a sequence of frames or images. Right? So it's a sequence of images which we have captured, and that's where the name comes from, like motion pictures. And like pictures in motion in a way. And so this is basically a sequence of images, which is what we want to compress. This is something which I found quite interesting when I was preparing for this lecture last year, which was that actually the first video was captured on Stanford's campus, and it was Leland Stanford's horse. You might have seen this video or image at some point, and they call it a video, but it was basically a few images of a horse, maybe 12 images or something, which they clicked. And the reason for this video capture was to really know if horses' legs are in the air for a fraction of a second or not. And that was the kind of the first video. So it's kind of nice that we are having this talk at Stanford, given the history. Right? Cool. Okay, so let's take a look at, this is just a sample video which we will work with during the lecture. If you look at, it's a jockey video, like again a horse. Just given the history, we are going to take a horse video and try to compress it. Now, whenever you look at a video, there are a couple of things to understand or look at, and the two numbers are the FPS and the frame size or the resolution. Right? The frame resolution is just the number of pixels along the height and width dimension, and here this is a 720p frame. At the same time, FPS is the frames per second. So that's the number of frames which you have, or which the video has when it was recorded, which is 30. Right? So it just tells you the amount of images which are there in this video. It's quite incredible. Today most of the videos are also captured at 60 FPS, so this is slightly old, but it just tells you that you are basically capturing relatively large images 30 times a second, and if you are recording a video for like 5-10 minutes, then it's going to be a crazy big file which needs to be compressed. Right? Okay. So far so good. Any questions as of now? Okay, cool. So let's try to understand this video a bit more. So what I'm going to do is that I'm going to use a utility called Media Info. It should be also, you can just install on your machines and look at this video. So this is a raw, like Y4M file is a raw video encoding file, and we can look at this encoded file to see what is happening. And so you can see usual suspects, like there is the resolution here, which is 120 cross 720 and so on. There's 30 FPS as we discussed. The color scheme is actually YUV420. I believe Pulkit might have discussed this in one of the lectures on why we use YUV420 color scheme, right? At the same time, one very interesting fact to note here is this 332 megabits per second bit rate. So that is actually the file size. If you're going to record, just store this video as it is, raw video, 1 second, it's going to take 332 megabits. Divide by 8 to get megabytes. But it just tells you that it's quite incredible. If I have to, stream this video to my home, I have maybe 100 megabit per second Comcast net at home. It's not going to play. The video is just not going to play, right? So it just tells us that, we really need video compression. It's not, our infrastructure can't really handle videos in the raw format. This is also much smaller video, like today we watch Netflix at 4K and so on, so it's going to be much bigger than this, right? So it just tells us that we need video compression quite a bit. All right. Okay, so let's see what if, I mean, let's try to use H.264 so to compress this video and see what file size we get, right? So I'm putting these commands at the bottom. So the most common way you will use, I mean, apart from just using some of the UIs, if you're using command line, then you can use FFmpeg, which is a very common utility to work with video, not just compression, like anything related to video processing. And here I'm using X264, which is one specific encoder for the H.264 codec. And I'm encoding this video at this parameter called CRF20. So CRF implies, you probably might have heard about this when JPEG compression was discussed, but CRF basically tells you like the quality parameter or the quality level. And 20 typically corresponds to like human imperceptible. So this is at a level where humans typically don't really perceive, and there is no, I mean, there are no distortions which you will perceive. And so this is at this particular compression level, right? And at this level, what we see is that already, I mean, the compression which we get is quite incredible. I mean, it's almost 50x. The video using H.264, we already get it down to 6.2 megabits per second, right? Which is quite incredible. And I'm not sure if you can see anything. Let me play the video. If you see any weird artifacts, at least I don't. So it's relatively good. I mean, probably there might be some artifacts in the fountains and so on, but it's relatively good, right? Depending on the application. So, okay, so let's try to go ahead. I'm going to use, again, the same command, an X264 codec, to encode it at CRF40. So this is a more aggressive compression level, and you'll see that, I mean, we get much better compression, right? It's 0.8, it's even 6x lower. But at the same time, and if I play the video, some of you might notice, some of you might not notice, but there are a bunch of artifacts which crop up. So I don't know if maybe at the head of the jockey, there are some like weird blocky artifacts which come up and which are kind of perceived. Even here, you can see on the legs, there are a lot of artifacts which come up at this compression level, right? So, I mean, of course, there is some, at least using X264, there is some limit. But we know that at least we can get this 50x compression using X264, right? So, okay, let's try to understand how we can get this, right? Okay, so now, as I mentioned, we are going to use all our past knowledge, whatever you learned in this course, to try to achieve this. And I know that, I mean, everyone is at this point familiar with how JPEG works. And so we are going to use image compression to go towards video compression, right? And so image compression we'll use just as a black box or as a utility function for in the beginning and see what we can do with that, right? So, okay, so maybe a quick question. What is the first thing you would do? Like, let's just say you have an image compressor implemented, you have the JPEG compressor which you implemented in your homework, and you want to apply that for a video, right? What is the first thing you would do? Any thoughts? Yeah?
Just compress each frame individually.
Exactly. Yeah, so the simplest idea, just from definition, like a video is a sequence of images, so let's just try to compress each frame independently, right? And if we do that, so, and we can in fact do that, and that's actually called iframe compression. You will see this term thrown around in video compression literature. It just means that if a frame is compressed independently as an image, it's called iframe, right? And so we can just compress each of these frames independently like an image, and that's iframe compression. And so let's see how good it does. So you actually see that on this video actually, if you just do image-based compression, just individually compress every frame, then we get a very, amazing compression. It's already like within almost half of the, it's not as good as if you use the H.264 codec, but just iframe compression of H.264, you get 9 megabits per second as compared to 6, what we got there, right? So, the results could differ. Like we'll see, I'll show a couple of more videos where there is not as much motion, and we'll see that if we just compress them as it is, then the compression is much worse with iframes. But on this video, because there is a lot of motion, we see that just iframe, just this simple idea which you mentioned, we are able to get within like 9 megabits per second, right? And so now the next question is, okay, how can we go from here towards the 6 megabits or even lower, right? So that's the next question to answer. Okay, all right. So again, this is the video compressed using the iframes. It's relatively good. Okay, so I'm going to show a couple of images and I'm going to toggle between them. And let's see if there is another thought on how to go forward. Yeah. So, yeah, I mean, the key idea or the hint is that, I mean, compression is all about removing redundancy. Like wherever you see redundancy, wherever you see correlation, you have to uncorrelate these things, right? So any, again, thoughts on what we could do to improve the compression? Okay. Okay, one hint, okay, yeah?
There's a lot of correlation between the frames, so if we do something like encode the first frame, then we can say, oh, the second frame shares a lot of the same components.
Yeah, that's right. I mean, both of these frames, if you look, they share a lot of common information, right? I mean, it's quite obvious. So if we have the frame 0 encoded as an image, then if you look at frame 1, then like this, most of it is just like shifted to one direction. So we could basically just copy paste most of it as it is. And if there is a small difference, that's what we could encode using like an image and so on, right? So that's what we actually do. So the overall pipeline actually looks something like this, that you take frame 0, frame 1. So this frame 0 is actually the encoded frame. I'm calling it frame 0. We find the motion. So here, like there's some motion. The logo is static. That's a different story. And then we basically find the motion, and then to kind of compute the frame 1, what we can do is that we can apply this motion on top of this frame 0 to get a compensated frame. And then we can encode this residual, the difference, separately, right, as an image. Is this clear? So this is kind of the broad idea of how video compression works, that you compress one frame as it is and then encode the difference in a separate way. And this mainly works because our frame rate FPS is quite fast. I mean, 1/30th is quite fast, and so the motion is typically much small. Like if you look at two frames separated with 1/30th of a second, typically they're not going to be different by quite a bit. So, all right. So this is actually what is called p-frame coding. So I mean, we spoke about iframe coding where every frame is independently encoded. This is the p-frame coding where the p-frame is the predicted frame. So what you do is that you first encode let's just say we start with the first frame. It's encoded as an image. Then you encode the second frame, the p-frame dependent upon the first frame. And then the third frame dependent upon the second encoded frame, and so on, so on, so on. And at some point, obviously, your prediction is not going to be great because every time you are doing this, there is some kind of noise added to it, and it might become a bit more expensive. So you refresh by adding a new iframe. Or if the scene changes, let's just say, I mean, when the horse is running, something else comes into the middle, then you can add another iframe, right? And so that's how typically the INP frame works. Right? Another one thing which I wanted to mention is this key int. So the key int, you will also see this term. It implies like the distance between two iframes. So that's the distance between two iframes or keyframes, which is 6 in this case. Right? Is this fine? Okay. Cool. So this is the overall block diagram for our IP coding, which is that we first find the motion, we encode the motion, and then we apply this decoded motion on top of the previously reconstructed frame. And that gives us the motion compensated frame. And then we take the difference and then encode this difference as an image compression, right? Okay. So now maybe another question is that, I mean, in the previous iframe coding, we also had image compression block, right? It was basically operating on a same image again and again. In this case, we have a much more complicated thing. Like there is this motion compensation and so on. And again, there is an image compression block here. So why do you think this should do better? I mean, even though we still have the image compression block here, right? So why do you think this does better? Or this should do better? Yeah?
The residuals should be very low entropy.
Yeah, good answer.
They should be mostly like space or
yeah.
with some artifacts.
Yeah, no, that's a good answer. So we know that image compression depends on the image itself. Like if the image is simple, then you are going to be able to compress it much better. If the image is there's a lot of things happening in the image, then it's going to take a lot of bits. And so the residual, as you mentioned, if it's simple, if it's all blank, most of it, then if we use something like JPEG to compress it, the residual, we should be able to do much better, right? So that's kind of the idea. That we are trying to extract out all kind of correlation before we use our image compression techniques here. So and that's what most of the video codecs do. Okay. All right. So let's now try to discuss how this. I mean, we already know this block. We already know how the image compression works, right? I mean, we looked at it. So let's first try to focus on this part here. Like, how do we really find the motion, and how do we encode it? Right? So the encoding part, I'm not going to discuss as much today, but it's kind of similar to what you have seen in the class. But let's look at how do we really find the motion. And so in H.264 and most of the traditional codecs, the simplest idea is that it's again based on correlation. So you take the reference frame, you take a reference block, and then try to move this block, try to check where this block matches, right? And wherever this block matches, you know the location of that block, that's the motion. Right? And so that's kind of the simple idea based on block matching algorithm. By the way, there are a lot of good resources from a past course at Stanford. Unfortunately, it doesn't run anymore, but Burn0 has a lot of good resources on the website, so do look at that if you want to really go into the nitty-gritty details of video coding. Right? So that's basically the broad idea. It's quite simple. You just take a block. Again, it depends on the algorithm, like what block size do you want to take, and how do you want to do the searching, and so on. But the broad idea is that you take a block, you try to match it, and wherever you get a good match, that's your motion. Right? And okay, so maybe here is some examples from again, if we apply the motion, as you can see here, like there is some motion. Most of it is static. There is some motion in these branches while they are moving, and we take the residual and so on. Now, again, I mentioned there are different strategies to do the block search, but I'll just mention a few. So here is full searching, where you can basically search across the entire image, which is obviously way more expensive. But the way in which most of the times people implement this is hierarchical searching. So what you will do is that, I mean, if you want to do block matching, you will actually start from the lowest level. Like you will downsample your frame by say 4x. You will do block matching there. Once you find like a coarse match, then you will again upsample your frame and find matches there, and so on, so on. So you can do this as a multi-scale just to kind of make the problem more tractable and solvable. And this is very similar to, I mean, a lot of the video processing which you will see today. I mean, in most of the video processing or even image processing uses image pyramids, which is very similar to this idea. Is this fine? People understand how the motion vectors are found? Yeah. And then, yeah, once you have found these vectors, you can just encode the difference. The differences are your motions per block, and then you will encode these motions. Right? Okay, so maybe let's take a pause, and I actually want to show you a sample encoded video. So we are going to use actually something called StreamEye. Okay, so even before we look at our jockey video, because the horse video is slightly more complicated, I'm going to look at this one. So this is a slightly simpler one because it's just smaller. Okay, let me. Yeah, so this is a software which, I mean, what it is doing is that it's looking at the encoded file and it's just trying to display all the encoded information in a much different way, right? All right, so here what it's showing is that it's showing the number of bits used per frame. So this bar chart actually tells the number of bits used per frame and like every frame here. So maybe one quick question is that like you see that there is this high bar here and there are these smaller bars after that, and again a high bar here and smaller bars. Any idea what is happening? Like why some of these frames have such high motion while some of them just don't have as much high motion? I mean, sorry, not motion, like the file size, the bits used for that frame is so high in some cases while not as much in other cases. Any idea? Like what are these frames? Yeah, that's right. Yeah, so in this case, actually, you see that, I mean, the iframe, which we compress independently, takes a lot of the bits. And after that, the subsequent frames don't really take much, as many bits. And in fact, that's seen here. So here it shows the number of I and P frame counts. The I frame is 2 frames, P frame is 14. But the number of bits used in terms of I and P totally is like just skewed towards I frames in this video, yeah, which is quite incredible to see. Right? Cool. So maybe let's look at some of these frames. Again, as here it's showing the. So this software is actually quite useful. You can also put it on your machines and see. It shows you the raw bit stream and a bunch of other information about every block. But here we are just showing the motion vectors. So as you can see here, I'm not sure if it's visible, but you can see the arrows which tells you the motion vectors in every frame and how it is going, right? And as you can see, the block size is quite different. It need not be the same block size. H.264 allows the block size to be, again, similar to BPG or which you might have seen in class. What people have seen is that variable block size works better because in some cases, if the area is not as much textured, you can have a much bigger block size, while in some cases you can have a much smaller block size, so on. So again, as you can see, we can see these motion vectors in this case. I also wanted to show the predicted. Okay, 1 second. Yeah, so here it's showing the decoded. At the same time, it's also showing the predicted frame, right? I think that you should be able to see some of the difference. So the predicted is actually like the prediction from the previous frame, the motion compensated frame, right? And you see some differences. Let's look at this frame. Like here, I see some difference here, like some kind of blocky artifacts here, and then it should be reflected in the residual. Like you see that part is. The residual, as you mentioned, it's quite sparse. It's quite, it's almost zeros. And then this residual is encoded using image compression-like techniques. So it's quite cool to see. You can spend a lot of time just staring at these and trying to understand. Cool. All right, let's get back. Actually, let's also see another video, which is the jockey one, which is our standard video. Yeah.
So for the compressing the residual frames, do we use a different image compressor or like some different parameters compared to the iframes? Because these do look different from like natural images.
Yeah, good point. So the hyperparameters which are used for encoding can be different, and it depends on the encoder. So actually for the residual frame itself, I believe the Huffman tables itself which are used the preset Huffman tables which are used are slightly different in this case. And also there are, the H.264 standard actually only specifies the decoder, so you will see that like different encoders they can do whatever they want. Okay, so we'll see another file which is jockey, but it's encoded at a very high bit rate. So we are encoding this jockey video at a much higher quality. And again here I just wanted to show